Hello everyone, in this video I'm going to be going over acid-base concentrations and just kind of go over some of the basics between acids and bases. I know for me personally, this is something that they didn't necessarily cover very much in high school. It was kind of like brushed over. So I figured that this would be a good one to go over because I know I personally even struggled in it. And it's definitely good to look up some videos on this one as well. Like I know there's definitely probably some good Orgo Chem tutor videos on this. Dave Professor Dave. I'm like Dave Professor. That doesn't sound right. No, Professor Dave. He probably has some good videos on there, but this is kind of like my little mini lecture and practice problems that I wanted to throw out there. So with acid-base concentrations, you're usually asked how much acid or base is needed to neutralize something. So usually in these problems, what you want to do is you want to make the number of hydrogen ions present equal to the number of hydroxide ions present, right? So in bases, you're going to see hydroxide ions, and so that's what, is going to be reacting. And then in acids, you're going to see those hydrogen ions, which we'll go over a little bit further. But that's like the general goal, right? In order to get that goal, we use that same concentration equation that we use, but this time we're doing acids equal to bases, right? So we do the molarity of an acid times the volume of that acid is going to be equal to the molarity of the base times the volume of the base. So yeah, that's basically what we're going to be using. Now we're going to look into monoprotic and diprotic things. So the first question is, why the heck is hydrogen called a proton? Because hydrogen's an element, it's not a proton. Well, it's actually pretty interesting because hydrogen is the first element on the periodic table. It has normally when there's no extra neutrons, no extra protons, no extra electrons, we're just talking about basic old hydrogen, like textbook hydrogen. It's going to have one proton, and I have my little key here so you can follow along. Protons are blue, neutrons are orange, and electrons are green. So it has one proton, one neutron, and one electron. When it forms as an ion, this is supposed to be +1 by the way, when it forms as an ion, it's going to lose that one electron, and all that you're left with is one proton and one neutron. So it basically just acts like a proton. Sometimes it might not even have the neutron, but most of the time we just say it's a proton because it doesn't have any electrons or anything. It's literally just a singular proton and a singular neutron most of the time. So it basically just acts like a proton. So that's why we call these acids diprotic, and like when we're talking about acid-base reactions, we say, oh, the base gained a proton, or the acid loses a proton. So that's how we describe acids and bases, right? So just kind of like as a general overview, acids are something that will give up H+, which is also known as a proton. And then bases are, we like to call this donated too. So you'll see that also referred to as proton donors. And then these will take the H+ protons, which we usually like to call acceptors. So we call these proton donors. Acids are proton donors because they give up a proton, and bases are usually called proton acceptors because they take the H+ protons, right? So going back to protons and everything, he did name these as ones to focus on, so I'm feeling that these are going to be the ones that we're most likely to see the acids wise on like a test. So monoprotic, we have hydrochloric acid, which is just HCl, and then we have HNO3. I'm not exactly sure the name of that, but HNO3 is another acid that we might see, and then HClO4. Yeah, HClO4. That is another one of the monoprotic. So these can only give up one proton because they only have one hydrogen. We're talking about like per molecule, they can only give up one. Obviously, if there's a mole of them, they can give up 6.022 times 10 to the 23rd hydrogens if they wanted to. But per molecule, they only are able to give up one. When we look at the diprotic, you can see that there's two hydrogens here. So this is actually sulfuric acid, extremely strong. Don't get it on your hands. If you take Orgo Chem, be careful with this. it will burn if you put your hand underwater. Just a forewarning. So if you get sulfuric acid, do not put water on it. Tell your professor, be like, hey, I have sulfuric acid literally on my hand right now. And they'll get baking soda, or sometimes they use like cat litter, but they'll get something to neutralize it, and you'll probably have to go talk to public safety. But be careful with this, because it will melt your hand if you're not careful, and if there's a high enough molarity. Anyways, this is able to give up 2 protons. So when we're doing the calculations, we want to keep that in mind, that this itself, one molecule of this, can give up 2 protons. So I guess I'll do a little bit of an example here. So if we have something like NOH, and we're reacting that with H2SO4, right? That's an S and that's a 4. I know it looks horrible, but just keep that in mind. So this one, we'll just kind of break this down as being 1 OH and 2 protons or 2 hydrogens, right? So now how many OHs will we need in order to neutralize this? We're going to need 2 OHs, because this will then have a charge of -2, and then this will have a charge of +2. That's kind of like another way that you can think of it. You want the charges to be 0, aka neutralize it, or you can think of it as this can give away 2 hydrogens, so it's going to go to one of them, and then it's going to go to another one. However you want to think of it. That's just like the thought process, I guess, that I have. And then let's moving on to let's think about it as we're talking about that. Here's a image, or like a explanation of an average acid-base reaction, right? So you have a base and an acid. A base is always going to have something positive, and then the hydroxide, and it's going to be added to something. It's going to be added to the hydrogen, which is positive, with something negative, right? You don't have to really worry about that, but that's just what it's going to look like. And usually you're going to end up with a salt and water. So we'll say that we have NaOH plus, we'll do Li. Oh, that's also a base. We'll do HCl. HCl, you react those together, you're literally going to get water and salt, which is weird to think about. You have something that, hydrochloric acid, if you have enough of that, like, that's going to really hurt you. And then sodium hydroxide, I don't exactly know like how strong of a base that is, which is another thing that you might want to look at. Let's look at that actually, how strong this base is. NaOH, pretty freaking strong. So probably could also do some damage. 2 things that can do damage literally just break down most of the time into water and salt. So yum, salt water, delicious. Don't drink that though, because probably won't end up good. That's assuming that everything works out perfectly, but in chemistry things don't work out perfectly, so don't drink. If those 2 get mixed together, don't drink it. So I kind of have like an in solution thing. So we talked about aqueous solutions and how they break down. So this would be positive, that would be negative, that would be positive, that would be negative. So these 2 go together, they react, and then these 2 react together, and then we get the salt and we get the water, because as you can see here, there's 2 hydrogens and 1 oxygen. That makes the water, and then the salt just gets added together. So that's just like another thing to think about as you go through these. There might be a problem on the test regarding that. Again, like, I don't know how the tests are. I don't make the test. But if there's a problem on there asking about like the reactions of bases, then you'll know that. Okay, so now let's get into a practice problem on this. This is one that Professor Sherlock had in class. So it says you have 25 milliliters of H2SO4 and 39.9 milliliters of 0.228 molar sodium hydroxide. What concentration of sulfuric acid is needed to neutralize the reaction, right? So we're going to be working with that same good old concentration equation, base, volume. Okay, so we're working with this, right? So we're just going to do this in general, and then we're going to look at the protons and see if like this is diprotic or if we have to worry about that. If we do, then we'll do a little bit of like, I guess, kind of like stoichiometry. I like to more so call it like a ratio to find it out, or dimensional analysis, I guess, easier way to put it. But let's put some of these numbers in, right? So for the acid, we have 25 milliliters, and we're going to find what the concentration we need is. So we don't have that concentration. So let's write that out now, because we don't have that. But we do have the volume, which is 25 milliliters, and that's going to be equal to the moles of the molarity of the base, which is 0.228, and the volume, which is 39.9 milliliters. Okay, so let's just do some math here. We have 0.228 times 39.9. So we get MA is equal to, just a second here. So I got about 0.36 what is molarity in? I'm like blanking, grams per milliliter. I think that's what it is. Molarity? Guys, no, that's bad. It's moles per liter. Don't moles per liter. But again, that like doesn't matter necessarily. So yeah, so that is 36 moles per liter would be needed, right, if this was a 1-to-1 ratio. But we can see here that this is diprotic, so we get 2 hydrogens. Cool. So now we have to worry about that, right? So what I like to think of this is that this is how many protons that we need. So we need 0.36 protons in this, right? Because if there were to be a molarity of 0.36 that's needed, we also need 0.36 protons. So I'm going to do protons, and then we have 1 H2SO4, and for each H2SO4 we get 2 protons. And then I'm just going to do the math there, and we get 182 about moles of H2SO4. And then that would be your answer. It's highly likely that we won't have to do this step, but again, if you do have something that's diprotic, which if we do, it would be H2SO4, at least that's what Professor Sherlock has said in one of his classes. But either way, if it has 2 hydrogens, you know it's diprotic. And then if it has 2 OHs, then you know, we usually don't work with something that has 2 OHs, but you would do basically the same thing. So you would divide just by how many protons are present, and there's your answer. Okay, so real quickly, we are going to now look at this other practice problem, which I made up. Hopefully it works out the way that I kind of want it to, but it says how many milliliters of 0.1 molar hydrochloric acid is needed to neutralize 50 milliliters of 0.3 molar lithium hydroxide. So you're going to do the exact same thing. You guys can pause this if you'd like to try it out. Go for it, but I'm going to get started here where we have the moles of acid times the volume of the acid, and that's going to be equal to the moles of the base times the volume of the base. So the moles of the acid that we're given is 0.1 moles, and we don't have the volume, so we're going to write VA. And the molarity of the base is 0.3 molar. 0.3 molar, and we have 50 milliliters of that. So again, we're just going to do some algebraic stuff here. We're going to do 0.3 times 50 divided by 0.1, and we are going to get volume of the acid will be 150 milliliters. I'm just going to think about this really quickly. How many moles? That makes sense to me because this is 3 times greater than this, so we really are just doing 3 times 50, which gets us that same answer there. That's just me doing it in my head, but this is like the best way to do it. Don't think of it like that, like this is the 100% best way to do it. That's just like a good way to check yourself, like, oh, does that make sense? Well, that's 3 times more than that, so then this should be 3 times more than that, right? Okay, so I'm also going to check real quick, make sure we're not dealing with anything that's diprotic or something that has 2 hydroxides. So this one only has 1. Awesome. This one also only has 1. Great, we don't have to do any stoic, and there's our answer. So that's my practice, and that's my little bit of explanation. Again, reach out with any questions, and thank you all.